Hi, everyone. My name is Jeffrey Vedder from Oak Ridge National Lab. I'm happy to be here. Thanks for the invitation. So tonight I'm going to try and talk a little bit about the high-level trends guiding our industry. You're here for 2 weeks. You're going to be learning about different programming models and different architectures and how to patch those together to get the systems to work. And what I hope to shed light on is what some of the overall trends are driving computer architectures moving forward. And this really isn't to scare you. It's just so hopefully you can start asking the right questions and prepare for what's to come. I did have an alternative title that I wanted to put up there. So the Turing Award winners from last year were Hennessy and Patterson. And the talk they gave during their Turing keynote was called a New Golden Age for Computer Architecture. And the question I have is, does that equal the dark ages for software and architecture and algorithms people? Because it's going to be really challenging moving forward. Architects are going off in many different directions. They're going to be changing much more frequently than we have in the past. And so choices of software systems and programming systems are going to be more important than ever. So let's take a quick poll first. And try to, we're not grading you on this, so try to be honest when you vote. So think back 10 years. How many of you would have predicted that many of our top HPC systems today would be GPU-based architectures? So, yeah, go back 10 years, 2009, how many people would think they'd be preparing for that? Okay, some experts, okay. So that's fair. So, that's an easy one. So the next question I have for you is a little bit more complicated. Think forward 10 years. 10 years from now, 2029. How many of you predict that most of our top HPC systems will have the following architectural features? I'll put the whole list up there, and we'll go through some of them, but again, I want your honest opinion about this. So how many of you think you'll have an x86-like multi-core CPU in your HPC system? Okay, the guy from Intel says yeah. Okay, how about a GPU? A reconfigurable processor like an FPGA. Wow, okay. A neuromorphic processor. Ooh, okay. 1. Oh, that's a lot lower than I thought. A deep learning processor. Wow, that's more than reconfigurable, I think. Quantum processor. Okay, we got some hopefuls. A RISC-V processor. Now you have to know what RISC-V is, but okay, I see about 10 hands out there. Okay, so some new unknown processor. We don't even know yet what might be in the system. Wow, I think that's the total. I think the answer is probably going to be, the cop-out answer, which is I at the bottom. It's going to be some combination of all those in an SoC. That was the fun question. Now, this is why you're here this week. Now imagine you're building a new application with 3 million lines of code and 20 team members over the next 10 years. What on-node programming model system do you think you'd choose and commit the entire team to? So there's a long list of options out there. And these options really depend on whether you meet your milestones and you get your science done. I'm not going to go through all these. I'm just going to illustrate some of the choices here. There are things like languages like C and Fortran and C++. Yeah, they'll probably be there. There are some nice templating tools and other schemes like Cocos or Raja that you might be able to use to hide some of that complexity. You have some proprietary solutions like CUDA and HIP. You have OpenCL and SYCL, which are even more open and sometimes more portable. Then you have directive-based solutions like OpenMP and OpenACC that try to hide some of that complexity and have the compiler do the heavy lift. And then, especially with deep learning, you've got R, Python, MATLAB, a lot of people using these technologies to hide that complexity. And then there are the domain-specific frameworks and even things we probably don't know about. I mean, how many people thought about TensorFlow 5 years ago, right? Or PyTorch? Not many people. And these things are literally being created in 18 months or a couple years. And so the point I wanted to get across is that, you know, the future is going to be much more uncertain and complex than it has been in the past 20 years. In the past 20 years, we had a pretty easy ride, in fact. Some solid standards like MPI, OpenMP, even pthreads, and some of those things were guaranteed across systems. It's not going to be that way going forward. So finished with the quiz, so let's move on with some of the motivating trends. So why are we doing this? Is it just computer scientists gone wild, right? Are we just trying to make things more complicated? It's not. So the contemporary devices are really reaching their fundamental limits. And you can go download dozens of articles that explain this, so I'm not going to go into it in detail. But certainly Dennard's scaling has ended, and Moore's law is certainly is slowing down. A lot of people think it'll be finished in the next few years for either economic or technical reasons. What I mean by that is if you just look at how much it costs to build a fab and the number of fabs and foundries out there, it's dropping precipitously, right? This chart from Wikipedia, or I think it's Wikipedia on the right, just shows how many foundries there were at different process nodes and where we are today, right? Samsung, TSMC, and Intel. Right? And one of those is a pay-to-play foundry where anyone can go up and pay them money and get a chip made. The others are a lot more proprietary in that respect, although they're doing more to open up as well. In the future, we don't know. Samsung claims they're going to spend $115 billion over the next 10 years to try and keep up this pace. But again, that's larger than the GDP of many countries, right? So it's going to be hard to keep that pace going. The other thing is you see this in just our industry, right? You see it in the cell phone industry with Qualcomm and NXP and ARM and all these other people, but you see it with NVIDIA and Mellanox, you see HP buying Cray. There's a lot of design costs, a lot of risk in the computing industry right now, and I would propose that it's because of this uncertainty around the trends that are slowing down. So, not to be a pessimist, I'd like to think of it more optimistically. I call it the sixth wave of computing. If you look at this chart, it's a chart from Ray Kurzweil's website, in one of his books, in fact, where he talks about the exponential growth of computing. And if you look at this, we've really been on an unprecedented curve. If you go clear back to the early days of electromechanical computers and relays and just move to the right, and this integrated circuit is what we've been riding for nearly 50 years, right? It's not just a transistor, but it's that integrated circuit is where we get a lot of the benefit. And so I'm proposing we're moving into the sixth wave of computing. If you're a computer scientist, this is a blast, right? There's all kinds of interesting things to work on. But for the people who buy the systems and the people who use the systems, there's a lot of uncertainty, a lot of important decisions that need to be made. While I was looking this up, I was also thinking about how long it takes to develop technology like quantum computing, and a friend mentioned to me, he asked me this question, when was the field effect transistor patented? And this is essentially the same one that started this phase that I showed you on this past slide in about the 1960s. Anyone want to take a guess? Shockley did in around 47 at Bell Labs is when they prototyped it. Does anybody want to think about when a patent was written for the field effect transistor? 1926, right? So sometimes it takes a long time for this technology to work its way through manufacturing and economics to actually get to the point where it can be something that's used in everyday systems. But what we see is, once it does make that transition, it can have a profound impact. Unfortunately, for this inventor, it had expired by the time, or he could have been a very wealthy individual. So during this transition period, there are three things that we're going to see. So the first one is we optimize the software we have and expose new types of parallelism. And so that's kind of what you're learning about here, right? HPC has really been on the forefront of that. MPI, OpenMP, other types of programming models to make it easy to build these scalable algorithms and applications. That's what you're learning about here. The second one is the emerging technologies. And so that's where we're looking at entirely new computational paradigms. There's quantum, there's neuromorphic, there's advanced digital. And those are the kind of the shiny new thing. If you follow this area much, you've seen a lot of discussion, a lot of funding for things like quantum computing. And so I grabbed a couple of these screenshots just to illustrate this. There's a huge amount of investment right now in DOE, in quantum computing, and some of the other government agencies. And it's even, in fact, at places like IBM and Google, Intel, and others that are investing, tens of millions of dollars or more in quantum computing. Now, this National Academy report came out recently, and basically it said, quantum computing is definitely something we need to be invested in, but it's going to take a while, right? They talk about not being a threat to RSA encryption for at least a decade. And there are also other things that they need to explore and basically applications that would drive this market, right? They need to see what those applications are. And so they're, funding a lot of projects, so let's hope some of those work out. The second one is neuromorphic, and I was surprised. I think only one person voted for neuromorphic when we were doing our poll. There's a lot of investment here too. I mean, if you look, Intel just had an announcement earlier this month about their new racks of neuromorphic systems based on the Lohe neuromorphic chip. And then in Europe, they've had the Spinnaker, and here are the IBM True North and Dana, and there's a lot of interesting work going on. One of the biggest challenges, though, with neuromorphic has been finding that killer application, right? People understand neural nets. They think they understand how the brain works well enough to emulate it with some of these systems, but they're still having some trouble finding a killer application for neuromorphic. But it still needs to be investigated. Then we have emerging memory devices. This is something we've spent a lot of time in, and in fact, you've got some of this in your cell phone, right? This is, for the longest time, we focused mainly on things like DRAM, which we all have in our systems, but more recently, the non-volatile memories have become really popular because they're used in cell phones and tablets and many other types of systems. And we have flash that you know and love that's incredibly cheap. We have 3D XPoint coming out now, and there are other options like that. Those are going to have the potential to fundamentally change the computer architecture in ways that may even change the way you write your applications. And so it just won't be an I/O interface to this non-volatile memory. It could be just persistent memory that you use persistent data structures through. And so that's fun. And then finally, and this is my short talk on the different technologies, but the new devices like carbon nanotube transistors are something that people are also investing heavily in. And there's a lot of benefit to this because it allows you to make the transistors, you manufacture them easier, you can stack them, you can put the resistive RAM on layers near the compute logic, and it all comes down to manufacturability. One of the benefits to doing these is that it lowers the temperature at which you need to fabricate the wafers. So that was the technologies, right? So that's just on the horizon. Some of those are things that are going to happen in the very near term, like I showed you a wafer of the carbon nanotubes. But quantum is a few more years out. And so in that meantime, what I'm going to talk about now is heterogeneous computing and architectural specialization. And I propose that's just another phase of this transition period that we're working through until we hit one of these killer new technologies that I just talked about, or some unknown one that we don't even know about yet. So what does architectural specialization mean? Well, CMOS is a fantastic technology, and if you look at the curves, there's almost no other technology like it in terms of the performance and the power that it's brought our electronics industry. We would need to use it differently, and so that's what's happening with GPUs and FPGAs and deep learning chips and everything. They're using the same CMOS process that the CPUs use. They're just using it differently. And so it's becoming more workload specific. And so that's where the idea of heterogeneity comes from. You have these chips that do special things instead of just having a general purpose processor. And you see examples of this in Amazon, Google, Intel I mentioned. Anton was a chip developed for protein folding. And then of course you have the GPUs and other accelerators out there. Those are all really popular now. Hot Chips is in a couple weeks. That's where a lot of the vendors like to introduce new chips. And it's amazing how many new products and new types of devices that they're introducing at this pace. And you already have examples of this in your phone. So how many of you have an Apple iPhone on you? If you have an A11 processor in it right now, it's got approximately 40 different IP blocks on it. And all of those, sometimes they compress video, sometimes they do audio. They have GPUs, they have different types of memory, they have different types of transceivers. A lot of that is already in your phone. So we already have precedent for this in the industry. And then there's the open source movement. I don't know how many of you know about RISC-V, but it's really an open instruction set. And on top of that, people were building open source software like GCC and LLVM. They're building open source hardware. So you can go to GitHub today and download the IP for different types of processors and basically do with them whatever you want and take them to a fab and get them built. Royalty free, right? Now there's of course people trying to do proprietary work on top of that, but that adds a whole new dimension, right, to this argument. And I like to sum it up in the words of Andreas Olofsson from DARPA, who has 2 projects focused on open source hardware. They're actually trying to design open source tool chains. So you basically do a few get clones, you make your SoC, you send it off to something like an Amazon website, and a couple weeks later you get back a box and it's got your board with your chip on it, right? Now that seemed like a real fantasy, and it still does, but that's very threatening. And imagine being able to just build your own chip that easily. Every chip could be different if you wanted to think about it that way. So what do we want to take away from that? So the transition period that I've been talking about will be really disruptive. There'll be opportunities and pitfalls. A lot of these changes will not be hidden by some abstraction layer. People will have to get in there and potentially change their algorithm. If you look on the right-hand side, what we have is a graph that I refined from IEEE's Rebooting Computing Committee, and it really looked at several of these technologies and really tried to rank how disruptive they were going to be at the different levels of the computing stack. And what you see there is something like a new carbon nanotube transistor, may just happen and you don't even know about it. Moreover, the people writing the applications or the apps for the iPhone or whatever, they won't know about it. The compilers will still work, everything will still function well. But then you move to the right and you start looking at things like neuromorphic and quantum computing, and you may need to really fundamentally rethink the entire way you use the system. For example, the D-Wave system does quantum annealing, and it's you have to formulate your input problem in basically a matrix that gets downloaded into this annealer. It runs for a few thousand iterations. You sample the data. You don't get back one right answer. You get back maybe a few thousand answers, and then you histogram those, and you get a high probability answer out of that. And so that's what I mean when I say you need to rethink the entire methodology for using that technology. And so that is what I mean by disruption. So this is DOE. This is the roadmap. It's not perfectly up to date, but what you can see here are the systems we've had recently. These trends are impacting us. Okay, you've already started to hear about some of the systems, Frontier and others. If you look at it, since about 2012, we've started to move to GPUs simply because we could get more power, more dense, on a more dense floor print than we could any other way. Some applications did well, some not so well, right? And part of that had to do with the immature software stacks and other issues. Now we're seeing deep memory hierarchies, right? Throughout the next couple weeks, you're going to be hearing about a lot of compiler tools and other libraries and things like that. How do you have to really think about these deep memory hierarchies to be able to exploit things like high bandwidth memory? And that includes this non-volatile memory that I mentioned earlier. In some cases, the non-volatile memory really fundamentally changes the way that you use memory. Sometimes it can be hidden transparently from you. Sometimes it really looks like a file system. And then finally, one of the other trends we've seen was plateauing I/O. The I/O bandwidth on a system like Summit is just about 2x what it was on Titan, which was 7 years ago, right? And so this is just plateauing, and it's going to cause problems. They're trying to use burst buffers on these systems now so that you can copy some of your state into that non-volatile memory on each node and then bleed it off to the slow I/O system. And that'll help some, but at the rate we're going to hit another major problem when we get to exascale in being able to get all that data off the system in any reasonable amount of time. The good news is some companies like Samsung are creating SSDs that are 100 terabytes or even more out of this flash, 3D flash that I mentioned earlier. And so that's going to, again, change the way you think about how you use these nodes. You could potentially have an exabyte of memory in your system in the form of these multi-hundred terabyte drives. And I know you had a talk on Frontier yesterday. That's our latest system that we'll be having in Oak Ridge soon. It's not an NVIDIA system, it's an AMD system. And so, we've had the luxury over the past 7 or 8 years working on NVIDIA systems that really did a lot to push the GPU paradigm, and they had a great software stack and tools that went along with it. I would say one of the strengths of their entire ecosystem was CUDA, right? When you download CUDA, you could run it on your laptop, you could run it on a server. It didn't change that much from version to version. That was really useful, but it's proprietary. And so when we make moves to the new systems, Aurora and Frontier, we're going to have to test some of those theories. So, recognizing this problem, about a year and a half ago, we had a workshop on what we labeled extreme heterogeneity, right? And the idea was to really focus the computer science community on some of these challenges. And it was primarily software challenges. We wanted to figure out how to make the systems more usable, and we're looking at the 2025 plus time frame. It attracted a lot of attention. We had, over 150 participants. We had people from labs, academia, and industry. We have a workshop report that you can download at the DOI that you see up there. But it went really well. And in DOE speak, these priority research directions are very important for funding initiatives and starting new efforts. And so I was just going to briefly go through these because they're what a lot of our community is going to be focusing on over the next few years. The first one is maintaining and improving programmer productivity. Now, right now, to write an application on some of our systems, you have to know MPI, you have to know perhaps OpenMP or pthreads, you have to know maybe in some accelerator programming model. That could be OpenACC, OpenMP offload, CUDA, OpenCL, or some other flavor, right? And some people actually mix these. And it creates a really a fragile application that's hard to manage and port and get performance out of. And it breaks the tools and all these other problems, right? And so we need to do better than that. We also need to do things like intelligent domain-aware compilers and tools. And this includes things like at our table, we had a nice discussion about machine learning. How do you bring the power of machine learning to bear on the programmability problem? And so that's something that would be a perfect fit for this. And then there's the composition of the different components and how you hook them together. One day you're running on AMD, the next day Intel GPU, the next day NVIDIA. This composition is going to be really, really important. And it helps if it's automated. Second, managing resources intelligently. You really need automated methods to introspect and learn what's happening in the system and do that automatically. Right now, when you run on that system, you're going to have 6 GPUs on Summit, and you can decide to create 6 MPI tasks and pin them to certain Power 9 CPUs and then have them manage individual GPUs. Now you go run on Sierra, and it's got a different number of GPUs and maybe different memory size. How do you, why should the programmer have to worry about that? We should find a better solution. The third one is a little bit of a surprise, but modeling and predicting performance. So, we buy all these systems through these elaborate procurements with benchmarks and all kinds of analysis of the system configurations. That job's getting a lot harder. I mean, if I give you, 20 applications and ask you to go run them on this architecture that doesn't exist yet, that's a risky proposition, especially when it's a $500 million system, right? And so that is something that we need improvements in. And then second, that modeling and predicting performance can also be used by this runtime system to help target what you're running on, right? And that's something that we'll be looking into. The fourth one is, again, this was kind of the surprise that the entire workshop found, and that was enabling reproducible science despite all this heterogeneity and asynchrony in the system. How do you even validate things when you're maybe running on an FPGA intermittently that may have a slightly different floating point representation than the GPU you just ran on? You may, in fact, not even know you were running on an FPGA because the runtime system scheduled it for you. How do you think about that? How do you preserve some kind of sanity as you're trying to reproduce these errors and other problems that you have? And then finally, facilitating data management, analytics, and workflows. So this is similar to the programmability and managing resources intelligently bullets. They're just at a higher level. You're thinking about almost a data center at this point, where you have petabytes of data that have to be moved around and scheduled to be where they're used. You need to be able to identify what hardware resources work best for the problem that you're focused on. Those are all things, again, that machine learning and some traditional methods could be applied to do some of that, to automate some of that work. And so that was the workshop. I wanted to mention a little bit about what we're doing. I know you're hearing a lot, you're seeing a lot of code, you're writing a lot of code. So I don't have any slides with code, but I wanted to put up kind of how we're approaching that. And this is the slide for our group. One of the things that we did a few years ago was create the Shock Benchmark Suite, and that's something that's available in GitHub. It is written in OpenCL, CUDA, and a few other programming models that you can download and use, and it actually uses MPI and some other tools so you can port it across platforms. A few other things that we're looking at include developing OpenACC for LLVM, and so we're starting to get to the point where we'll upstream that in 2021, hopefully. There's some other work going on in non-volatile C, and the idea there is that as you do in regular applications, you allocate memory and free it as you use it. With our language extensions to C, what you do is you actually get a pointer to non-volatile memory. And then as you read and write to that non-volatile memory, it's made durable by your system. And we have transactions, and so that's supported, so you don't have to worry about corrupting data structures of that memory. And there are several others here. This is all in support of this idea of really thinking about experimental computing. I'm a computer scientist by training, so I think this is a fun time. But I think more broadly, our whole community needs to be thinking this way, where you have things like carbon nanotubes or quantum computing, and how we move it from this traditional framework of what's called TRLs, technology readiness levels, and kind of push them up where they'll actually end up in one of our supercomputers. If you look at the green arrows down at the bottom, you know, it just really gives you a feel for where the technology is classified in that TRL level. You know, a bench system is just literally that. You know, you have a liquid helium refrigerator you're running some cryogenic processor in, and you have to, you know, hook probes up to it and all of that stuff. The emerging technologies, on the other hand, are things like FPGAs. We really don't have a large FPGA-based system, yet I think that was like the second or third highest choice among you in terms of next generation technologies. Now, one of the problems with FPGAs is, of course, programmability, and the compile times can be horrible, and those things. But people are working on those. So you know, I predict there will be a reconfigurable computer in the very near future. It may not be in the U.S., in fact. The other thing is RISC-V. So RISC-V is really trying to make that transition. It's in emerging area right now, but it's really being used for microcontrollers and you know, small processors. I just saw Alibaba announce today they're going to release their code for a new out-of-order processor based on RISC-V. And so they are investing in that technology. So the last thing I just wanted to mention was that if you're interested in these technologies, we have experimental computing labs. So when you go home, if you'd like to experiment with some of these technologies, we have a lot of them available. We have you know, a variety of GPUs. We have the Apache Pass, Intel Optanes, both types of FPGAs, as well as a variety of SoCs, including Zinc from Xilinx, Qualcomm, and a few others. And it's open. All you really have to do is write a short project proposal, and you can apply for access to some of these devices if you want to experiment with them. And we usually grant projects on 3 to 6 months. So if you have something that fits in that time frame, please take a look at it and let us know. So let me summarize. I know you guys have a lot of code to write tonight, so I don't want to go on too long. I can't believe you make them work after dinner, though. It's for fun. Yeah, okay. That's brutal. The takeaway messages. So Moore's Law as we know it is definitely ending for either economic or technical reasons in the next decade. And I'll say 2025 just to put a number on it. You won't see any banners from anybody saying Moore's Law is dead. It'll just take forever for chips to come out, and they'll be more expensive, and companies will go out of business because they spent all their money on CapEx, things like that. On the other hand, CMOS is fantastic, right? Like I mentioned earlier, it's this technology unlike anything the world's seen. It's going to continue. Even if we stay at 7 nanometers from here on out, there'll be a lot of fantastic stuff we can do. It'll be architected differently, and that's the main differentiator a lot of companies will use to separate themselves from others and try to be quick to market with solutions like deep learning, for example. Parallelism, that's going to continue. We have, I wanted to mention this because HPC has really been at the forefront of this, scaling up with MPI and doing parallelism. We really pioneered a lot of that, and I'm proud of it, and I think you guys are learning a lot here, learning about the programming models and architectures that you're learning about. I do think we need to be a lot more aggressively exploring these emerging technologies. Sometimes, they're bleeding edge, right? They have immature software stacks. They have, problems. You need to do firmware update every week. There are things like that you need to work on. But we need to start now because it may disrupt the entire software stack. Again, tremendous opportunities and challenges in designing and deploying these technologies. There's a lot of opportunities, especially for programming models. You should ask the people you hear from over the next 2 weeks with their programming models how they're addressing some of these new technologies. Things like GPUs and FPGAs even have some answers. Some of the others are a bit more of a research topic or open question. So I'll finish there. Start exploring these new technologies as soon as you can. Use your own lab. Feel free to contact us. But the future is in extreme heterogeneity. Thank you.